Alright guys, so we're going to go ahead and get started just to be cognizant of everyone's time today. So, as per usual with what I did last summer, we always save our questions until the end. So if you have something you want to ask one of our speakers, go ahead and write it down so you don't lose that thought. And we will go ahead with our first speaker. So, happy to introduce our first speaker, Michael Bailey. Michael, if you want to go ahead and come on up here. He's a senior neuroscience major here at the college, as well as an international student. He's had multiple opportunities to go perform research outside of Maryville College. The first one was in the summer of 2023, right? So summer of 2023, he was at Huntington Medical Research Institute out in California doing some cool work there. He's also served as a STEM Success Center mentor this semester and will next semester, as long as we'll have him back. Or he'll have us back, I should say. And he's also been our first neuroscience major to do that, so we do have support for some of those upper level courses that maybe we didn't in the past. Today he's going to be talking to us about the work he did at Rutgers University, involving the effects of CNS regulation and development by plexin and semaphorin signaling.
Today I will be talking about my research internship that I recently did at Rutgers University, and the title of this presentation is Plexin and Semaphorin Signaling as Key Regulators of Central Nervous System Development. So for our agenda, today, I will be introducing you to the summer research internship that I did, as well as some background information into the proteins that I worked with, the research question that I addressed, the techniques, and then finally the results. So the Rutgers University Summer Research Institute basically gives students, undergraduate students who are majoring in various STEM disciplines, the opportunity to work in various faculty labs. And they have opportunities for students majoring in neuroscience, mathematics, chemistry, psychology, biology, and just a wide variety of STEM disciplines. And for the 7-week period, I worked in the Neuronal Morphology and Connectivity lab under the guidance of Dr. Tracy Tran, and basically her lab focused on embryogenesis, so basically how neurons are formed and develop. So what are semaphorins? Semaphorins belong to a class of glycoproteins, and there are 8 different subfamilies. They are ligands, so that means that they bind to a receptor, and they have important roles for axon guiding and for the growth and development of the central nervous system. Plexin serves with neuropilin as a co-receptor for semaphorin signaling. So basically, semaphorin will bind to neuropilin, and then neuropilin would work with plexin in order to inhibit extracellular signaling. So this complex is very important for axonal growth, signaling, and guidance. So my overarching research question was that since semaphorin is a messenger and basically plexin is a co-receptor, what would happen if we deleted the plexin A1 gene? To delete the plexin A1 gene, we basically use this cutting-edge scientific technology, and it's called the CRE-LOCK system. So basically, one mice is injected with a CRE enzyme, and the CRE enzyme binds to a specific promoter, so that enables the gene to be deleted from a specific region of the body. So for example, in the spinal cord by itself. And then another mice is flanked with their gene is flanked with 2 LOXP sites. And basically when these mice reproduce together, some mice have their genes deleted while the others have their gene present still. So because we normally don't know what mice has their gene deleted, we use this technique that is called polymerase chain reaction and gel electrophoresis. So basically it shows us what is the genotype for each animal. So on the first animal over there, you can see that the wild type band is present. So that means that the animal has both copies of the gene. For the second animal, both the wild type and mutant bands are present, indicating that one copy of the gene is there and the next one is not. And for the third animal, only the mutant band is present, indicating that the animal has both copies of its gene deleted. Following polymerase chain reaction, we then did cryosectioning, which is basically thinly slicing tissue sections into small sections that can be loaded onto a microscopy slide. And we typically do this step before immunohistochemistry, and we use a cryotome for this. Oh, yeah. So that should read immunohistochemistry, but I don't know why. Yeah. So immunohistochemistry is basically a technique that is used to identify cells and proteins of interest. And the basic principle is that an antibody will bind to an antigen, and this is normally a two-day procedure. So on the first day, we would apply the primary antibodies, which would bind to the antigen of interest. And on the second day, we would apply the secondary antibody, which will bind to the primary antibody. And typically, the secondary antibody has some molecules that allow it to illuminate through a microscope. So our results for our plexin A1 knockout spinal cords, right? Oh. Yeah, right there in yellow is a part of the spinal cord that's called the ventral commissure. So a lot of axons are being projected across there. So in our plexin A1 controlled mice, a lot of axons are crossing, but in our plexin A knockout mice, there's a significant thinning of the ventral commissure. So this suggests that plexin A1 is indeed important for regulating the guidance of spinal commissural axons across the ventral midline. So we also deleted plexin A4 from a specific type of neurons, and these are called pyramidal neurons, and they're located in the frontal cortex. And on the left, we have 6-month aged mice, and on the right, 18-month aged mice. So in our plexin A4 control animals, as age increases, then dendritic complexity decreases. However, in our plexin A4 knockout mice, as age increases, there is no further change, and we are suggesting that this is because the animals don't have the gene in the first place, so deleting it cannot cause a significant reduction. So I also briefly looked into another protein, and this is called RAB11. It is not directly related to plexin semaphorin signaling because the two previous ones were extracellular, and this is like an intracellular trafficking protein. So we basically deleted RAB11 A and B from a specific type of neuron known as Purkinje neurons in the cerebellum. And when we deleted RAB11, as you can see in the wild type cerebellum and the knockout cerebellum, the cerebellum decreased in size, as well as there is significantly less Purkinje neurons in the knockout mice. So broader implications of this research: the plexin semaphorin signaling is implicated in autism spectrum disorder, as well as motor disorders and memory. So by understanding these mechanisms more clearly, maybe we can develop better treatments that targets these neurological conditions. And my acknowledgement.
Thank you, Michael. That was a fantastic look at everything you've been up to. I'm sad that we didn't have you here to do your, last year to do your presentation related to the stuff you did at Huntington. Do you mind, real quick, what was that related to? Was it similar, or?
It was kind of similar. It was like mainly looking at divergent interneurons and how they migrate.
Okay.
That was more so like the brain. We were focusing more on the spinal cord.
Okay. So for those of you that couldn't hear, his other work was more focused on what was happening in the spinal cord, correct?
No, this
Okay, and the other one was more focused on the brain, and this one's more focused on the spinal cord, but still related to some migration of some different molecules. right, so many of you I know our next speaker, who is both a member of the Computer Science Club as well as a TA for Computer Science 130, so a lot of you have had his assistance at some point or another. It is Kylind Reagan, a junior computer science and mathematics major, and today he's going to be speaking about his role investigating vehicle hacking. Some of you over the summer were fortunate enough to go see some of these departments that he was working in at the ORNL laboratory, so some of it may hit home for you. And I should also mention that this research was partly completed in conjunction with a partnership between Maryville College and ORNL, and that was using some FIPSE grant, or Funds for Improving Post-Secondary Education grant, that was gifted to us via the office of Tim Burchett.
So as Brett said, I got this internship from the FIPSE grant. So how it started, Dr. Siopsis last spring contacted some students, asked if they were interested in a position at ORNL, and we got to talk to some of the mentors, learn about some of their projects, and pick what we thought was interesting. So what I thought was interesting was this project by the Vehicle Security Division under the National Security Sciences Division at the lab. And what they were focusing on was vehicle hacking. So when you think of vehicle hacking, you might first think of something like maybe a Bluetooth hack, or maybe a Wi-Fi hack, or if you're familiar with what happened about a decade ago in Europe, you might know of like the vehicle-to-vehicle or road-to-vehicle things that happened across Europe, some of the hacking. But that is not our focus. Our focus was on this thing called a Control Area Network Bus. Now what the CAN bus does is it reads messages and communicates with electrical control units, ECUs up there, and they can control anything in a car, from a radio to your steering if you have drive-by-wire, to like smart brake or smart steer. Anything like that is controlled by an ECU. So what the CAN bus does is it just reads these messages and converts it similar to how a computer would. It reads it in binary and will tell the car how to respond to certain messages. So one problem with the CAN bus is that it has no validation at all. There's no encryption, nothing of that sort that's needed for vehicle security, and you can send messages to a CAN bus. This normally is not a problem because CAN buses are protected and your car, they're inside your car. But for semi-trucks specifically, they're on the outside of the car, accessible by anybody, and luckily for hackers, they're very conveniently colored differently than the rest of the wires, very easy to find. And the reason why CAN bus is so poorly, security-wise, is because it's left to manufacturers, but they don't do anything, so. So here's SHIELD. This is ORNL's answer to the problem. What it does is it's an intrusion detection system. CAN buses are very, very predictable. You know when a message will be sent, you know about what it will look like. So if something is different, it's very easy to find that and decide something should be done about it. And so one problem with SHIELD in particular is that it uses Socket CAN for testing. Now what Socket CAN does, it's a Linux-based real-time CAN simulator. This means that what it does is it processes the messages from a CAN data source and then outputs what it reads. But as you can guess from how I described it, it requires Linux, which means that there's some setup if you want to get it onto a new system. It's real time, which is way slower than what you'd want from something you're using to test your software that is doing this. And it could take hours to test to run the unit tests. Which means if you want to do any tiny change, you have to wait hours just to check and make sure that it worked properly and didn't do anything wrong. So so my job this summer was to find a solution to this problem. It was to make unit testing way more smooth so they could actually change things without having to worry. And here's my solution. It's called FTL CAN Player or Reader. It doesn't really matter. My idea for the new simulator is, what if instead of simulating an actual canvas, processing the messages, doing all that, which can lead to inaccuracies and all the things we discussed before, what if we just read it like a file? And so I got to work on that. In theory, I thought, this should be faster. This should be way more accurate. We're just reading it. Shouldn't have to worry about like time, the messages themselves. And the good part too is that it would, in theory, only need Python, right? You're just reading a file. Python can read files just fine. So let's, and here is the results. So you can see it did exactly what I wanted it to do. It's faster than real time. It keeps the original timestamps, as you can see up there. The timestamp is different. The IDs are different. This is because of something in computer science known as an overflow error. FFF is a bunch of ones. 7FF is also a bunch of ones, but it's a much shorter bunch of ones. So, so SocketCan is cutting off the actual ID. I don't know if this is a difference in trucks or if it's just how SocketCan processes it. It's unclear. Over here you can see it kind of got cut off, but the channel is different. VCAN is virtual CAN, and CAN is, that just shows that it does indeed come from a real CAN. Nothing is being processed. The timestamps are different. This is the original timestamp. This is a new timestamp. This is in Unix time, which means this is seconds from, I think, 2000 or something. So you can see like this is much earlier. And here you can see it's about 100 times faster. This file was only about a couple hundred lines long, a very small snippet. Some of the shorter files that were actually used for testing, hundreds of thousands of lines long. So you can imagine this will save quite a bit of time, and it did. The overall timing went from hours to run tests, as I discussed before, to only a couple of minutes, which I think is a major improvement and really good. So here's what I gained from my internship. I got a lot of knowledge about the industry. One of the best things I think I got was getting to read code written by people who've been in the industry for a long time. You learn a ton about like what you should do, and I think I got way more out of that than most things of the internship. It's just nice to see like, what do people do? Unit testing, very big in computer science, means you'll run into way less errors, way less just like problems in general, and it's much easier to test using unit testing than it is to manually test every single file. I learned a lot about legacy systems. This is a big thing in computer science. A lot of older machines run on things very similar to CAN. In fact, a lot of things use CAN bus, like elevators, roller coasters, old medical equipment uses CAN bus. So like, you can imagine that this has a lot of applications outside just cars. And also, ORNL has a bunch of other things outside of just the internship. You can go to a lot of presentations. I took a tour of the additive manufacturing facility, which is very nice. I got to learn a lot about that, which is something interesting. And these are all open to students. You can go to them. They're very nice. And also, I got to work with a lot of people who I'd never get to work with otherwise. I got to work with a lot of classmates who I had not really known before this internship. I got to meet a lot of mentors and people like one of my mentors. It was on the first slide. I had all of my mentors listed, and Luke Koch, who I had discussions for, I got to work more closely with, and that was nice getting to know him. And speaking of, and so here's my thanks. Thank you, Dr. Siopsis, for providing the opportunity, and the FIPSE grant for also providing the opportunity. Here are my mentors. Luke Koch, I just mentioned. These two are the people I work directly under. Great people. Got to work a lot. Jeff wasn't directly over me, but he's over like the division. So I got to work a lot with him, learned a lot from him. He helped me out a lot during this internship. And if you're interested at all about what I talked about in this presentation, the Car Hacker's Handbook by Craig Smith is a great resource. It goes into a lot more than just CAN. It goes way more in depth into vehicle to vehicle, like I mentioned before, and then like Bluetooth, Wi-Fi, all of that. And so it's a great resource. I'd really recommend it. And if you get a chance to do something similar to what I did this summer, I'd say you should definitely take it.
You can go back to your first slide real quick. I'm sorry, I realized that as soon as I got up there.
Yeah, so here. These are the mentors.
Okay. Thank you.
And one of the cool things you'll note about that is that he referred to all of those persons with doctorates by their first name, which was one of the cool things about working in the industry and at ORNL. Like, your degree becomes less important and it's more what you know and how much effort and capability you have is what they're after. So you were considered an equal while you're there because you're working on the same project, and that's a pretty cool thing. Actually start this one at the first slide. All right, my next speaker probably doesn't need an introduction for most of you. I know a lot of you started at the same time as Thomas Rude. Thomas Rude has been a member of the soccer team all 4 years while he was here. He also, this year, has been acting as a STEM success mentor, but previous to that, he's been working in Noah Bowman's various call them academic services and all of those different spaces, so I'm sure you all have seen him around. He's a senior mathematics major, and he also worked in, I don't know that it's the exact same division, but on vehicle hacking and vehicle vulnerabilities at ORNL this summer. His work was also completed in conjunction with some of that FIPSE funding that I mentioned earlier, and without taking up any more of his time, I'll turn it over to him.
Yeah, so as Brett kind of said earlier, shout out to Dr. Siopsis for getting that funding, because I actually did do a lot of work with both Kylind, and I see Kyla back there, she was also part of the group. But so while he did more of like the physical, actually working on the trucks, mine was more of a research based, and it was looking at if you can use AI to sort of hack vehicles. So just to sort of like background, obviously we're working at Oak Ridge, and there was a lot of projects going on at Oak Ridge. Some we were allowed to see, look at, and some we weren't allowed to know about. But we were working in the cybersecurity division, and so as a math major doing cybersecurity work, I was very nervous when I started because I only had like the first computer science class, and so I wasn't too confident in my ability, but everyone there was like super nice. They helped me learn a lot of information that I needed, and so it was kind of cool just learning a new skill set as I worked. And so those were sort of the departments that I mostly worked at, was cybersecurity research, AI, and then threats to vehicle safety. So first I'm going over some like background information, just so that way you know more what I'm talking about and can understand it more. So first thing that we were working on were large language models. Now, I'm pretty sure most of you here have used ChatGPT or know what that is. ChatGPT is a large language model, and it's basically a type of artificial intelligence that's able to generate, understand, and manipulate the human language. Now, the cool thing is, if you ask ChatGPT, hey, how do I hack an 18-wheeler? It'll tell you, this is unethical and illegal, so it won't actually give you the answer. But anyone with enough time and money can make large language models. So someone that's less ethical and doesn't care that's illegal can make a program similar to that and ask it the same questions. So Sam Hollyfield and some of the other mentors that Kyla mentioned, they were concerned like, hey, can we actually use AI to tell us how to hack vehicles, but not just hack vehicles? Can they come up with new ways to hack vehicles that we hadn't thought of yet? So they were trying to get ahead of the curve and just make sure things are safer before they got worse. So yeah, so those are some of the things large language models can be used for. But one of the limitations for large language models is they're trained on a lot of public data, so like books, websites, things like that. And after they're done training, they don't add new information. So like, say you have a company or a hospital records, things like that aren't open to the public, like that private information is not going to be in large language models training. So companies will either have to make their own large language model, which takes thousands of hours and millions of dollars, which most people don't want to invest in, or you use a RAG, or retrieval augmented generation. So what that does is you create your own like data set, database with all of those documents that only you, or in this case like Oak Ridge, have access to. So you create that data set, and then you combine a large language model like say ChatGPT or some of the other free ones that you find in the internet. You combine those two, and then the RAG will be able to give you answers to questions that the large language model without the RAG wouldn't be able to answer. So like, say if I asked ChatGPT, what's my dad's name? It wouldn't know because it has no access to that data, but it say there's a RAG with that information in the file, it could figure that out that way. So that's kind of the way around it. It's a lot cheaper, faster, and so I kind of learned how to make a RAG pipeline. And so that was kind of the goal for the summer, was to first create a RAG that was capable of looking at vehicle vulnerabilities, so that way the people at Oak Ridge could use that, and then to test that RAG to see if it could not only identify ways that we already knew how to hack vehicles, but if it could come up with new ways to hack vehicles, that way we could already start planning countermeasures for that. So then I started working in the Jupyter Notebook or Jupyter Lab. It's basically this virtual environment that allows you to code for RAG and other like LLMs, so like data science, computer science, and then machine learning. It's a very useful environment for that. That's right there is just a sample of some of the code that I needed to add to the computer, so that way the notebook and other things would actually run on it. So if I didn't import all the like extra embeddings and information, the RAG wouldn't work. So there was a lot of trial and error, just knowing which things I needed to add to have the file work. But after that, I started building different RAGs and just testing them, because not only did they want a RAG that could work, they wanted to see scientifically which one was the best one. So the first one I made was using a large language model with Dolphin/Minstrel. So at first it was pretty easy when I used like a small data set. It was just fast, it gave nice, clear answers, but when I added the full data set with all the information on hacking vehicles, it started having problems with what's called hallucinations. That's basically when the model just makes up an answer because it doesn't know the right answer. So it's kind of like a kid, you ask it a question, the kid doesn't know, so it just says something. That's not very useful when you're trying to like test something or see if it can actually hack a vehicle, because if it's just making up random stuff, that's not going to help you. So then I tried to fix that with prompt engineering. That reduced the amount of hallucinations in the prompt, so it started improving the outputs, but I wanted to see if I could make it better overall. So then I started using different large language models, which is kind of the nice thing about RAG, is once you make the pipeline, you can just change which large language model you're using, and it'll give you different results, which was kind of nice. So then I used Llama 3.1, which was actually made and came out this April, so it's sort of the newest model out there, which was kind of nice. And so the first couple of times it struggled to get the right answer just because it was kind of new, but then once it got the right answer and it knew it, it kept giving like that answer, so like it wouldn't change the answer, which was really nice. The answers, they were shorter than the Dolphins, but they were a lot clearer and easy to use, and most importantly, they were correct, which was what we wanted most of all. Unfortunately, as the summer kind of dragged on, I had to start soccer season in school, so I wasn't able to add memory to it yet. Memory is just the part where it remembers the conversation. So say you're having a conversation with the machine, it'll remember what you said earlier. So if you ask it a question about something you asked earlier, it'll know that and it'll give you a response with that. So without the memory, it's just answering those like individual questions without remembering anything that was said later. So that was just like a nice next step that I wanted to add. But basically what I learned was, or what I'd gotten to, was the point where, yes, it can look in the data systems to find ways to like hack vehicles, and it could find where systems were vulnerable. We hadn't gotten it to the point where it can tell you new ways or find new ways yet, but I'm currently working on that more for senior thesis, so update next couple of weeks when I have to present again for CEOPSIS. But yeah, that's sort of what I did over the summer, and it was really interesting because a lot of the mentors that like Kylind and Kyla had also were just like, yeah, this is like pretty good work, and like they were thankful that they didn't have to do the work to get it set up. So yeah, that's basically what I did. So any questions for us?
We'll go ahead and have the rest of the speakers come up and we'll sit there for questions for everybody. So what questions do we have for our guest speakers? A lot of really cool projects, some overlapping, some different than probably anything our students have seen before. Wait, what?
What's the difference between the REG and fine-tuning an AI model?
So
Oh, it's the slide that.
oh. Hello. All right, cool. So the main difference in the fine tuning is the amount of time and money into it. It costs a lot more to fine tune or tweak a large language model for that company's specific use versus if you do the RAG method, it's a lot cheaper to do, and then you can you only have to edit the RAG to suit your needs versus you have to edit a lot of the large language model. That's the main difference. Both do work, it's just one's cheaper, so people tend to go with the cheaper option. Yeah.
Okay, so I think it could apply to all three, but whoever could answer this specifically by itself. Like, when you take the internship, like there must be some sort of aspect that you didn't know or just needed to learn. So like, how did you make sure that you learned that as soon as possible and catch up on the job?
We can start with Michael on this one. I think I think all of you could add, your perspective on this one actually.
So for my opportunity, they were really set on ensuring that we knew exactly what we were supposed to know before we started doing the work. So it was a training opportunity more than anything. So they didn't really expect us to know everything prior to doing work.
Yeah, kind of to piggyback off that, one thing was to not be embarrassed to ask questions or to ask for help, because when I got there and there was something that I didn't understand or I wasn't sure about, I was like, hey, is this right? Or like, what's wrong with this? And they're like, oh, you need to do this and such and such. And so then I just kind of made a note of that and was like, so next time I would know. But yeah, just not being afraid to ask for help, because everyone was like really happy to help me, which was nice. So yeah, just not being afraid to ask for help when you need it.
So for me, how the internship went is the first little part of it. They basically gave me a bunch of resources and they were like, here's what you'll need to know beforehand, and if you have any questions, come to us. And so that was that. It was just like a lot of learning at first, and then getting into the actual code. So that, yeah, that's good.
Question, Michael. So making the knockout mice, that is a long and cumbersome procedure. What parts of it did you actually do with your hands? So there's, because there's like the designing of the knockout, and then you're doing it in the cell lines, and then putting it into the mice, and then the husbandry with the mice. So.
Yeah, so like that was predominantly done by the PI, but I actually had to know the exact procedure at first. In relation to that, it was just basically I visited the vivarium and like actually see them being like reproducing. So it was just mainly the end product.
Okay, just wondering. If there's a lot to it, it takes months, yeah, or years. Yeah.
Continuing on that for Michael, like, so how did this inform maybe what you want to do next, or has it like changed your trajectory? Are you looking at pursuing grad school maybe at that location or anything like that?
Yeah, I'm looking to pursue grad school. I'm actually applying now, so hopefully I get in somewhere.
Actually, can we ask all of them that more or less question? Like, how has this informed where you want to go from here? It can be positive or negative, that's okay, but What did you learn about what you want to do or directions you want to go?
Well, the thing that I kind of learned the most was when I was working with Luke. He told me how he got his bachelor's in math, then he got a master's in engineering, and then he just, as he was helping us over the summer, got his PhD in computer science. So I kind of just learned that even if what I want to do changes, he's still in a successful role and is a pretty successful person, pretty smart. So being open to change, and then just, you don't have to stick with one thing the whole time. You can change and get multiple degrees, which was kind of nice to know that, because that's kind of was my plan, to get a bachelor's in math and a master's in engineering. So seeing someone who did what I want to do and is successful was just nice to know. It was kind of reassuring.
My internship, it really inspired my love for like cybersecurity. I didn't really know much about it before going in, but going in I learned a ton of things and I really enjoyed a lot of it, like actually working on the truck, like to like learn what messages it has and like trying to penetration test and like figure out what's wrong with it. I really liked that, and so I'd be interested in doing something like that for a full career. So I guess this.
We have time for a few more questions, several more questions actually. What do you guys want to know about what they did, deep dive, or something maybe?
When you were a freshman, is this the kind of work you expected to do, or would it have surprised you?
I didn't really know what I wanted to do when I was a freshman, and I honestly didn't really. I mean, I guess I don't entirely know now, but yeah, I mean, I didn't know much about cybersecurity or anything, so I guess I didn't really expect this.
Yeah, I'm gonna just say no. I was not expecting that at all, but I was still glad that I did it.
No, I didn't expect this either. I got my first internship last year in 2023, and it was like partially because I wanted to go to California, and then yeah, and then I just like really fell in love with research afterwards.
What were you planning to do prior, Michael?
I just chose neuroscience because I was interested in psychology and like a little bit of science as well, but I did not think I was gonna like go in research.
Do we have any final questions? All right, then let's give our speakers a big round of applause.